So in this lesson, we are going to look at the continuity of functions of two variables. Now, a function of two variables f of xy is said to be continuous at a point AB in its domain if the following three conditions are satisfied. That is, 1. If the function is defined at the point AB, or if f of AB is defined. 2. If the limits of the function f of xy as xy approaches the point AB exists. And then 3. If the limits of this same function f of xy as xy approaches the point AB is equal to the value of the function at the point AB. So if all these three conditions are satisfied, then it means that the function is continuous. The function is continuous. It is continuous at the point AB. If all three conditions are satisfied, then it means that the function is continuous at this set point. Now, a function which is not continuous at a point AB is said to be discontinuous at that point. A function which is not continuous at a point is said to be discontinuous at that point. Now, in addition to that, even if only one of the conditions is being violated, then it means that the function cannot be continuous. Even if one of the conditions, either 1, 2, or 3, is violated, then it means that the function cannot be continuous at that point. And if a function is continuous at every point in an open set D, then we say that the function is continuous on D. And then if a function is continuous at every point in the xy plane, then we say that the function is continuous everywhere. So let's try some examples. So given two functions, f of xy, that is 1, f of xy is equal to 4x squared times y minus 3x times y squared. And then 2, we have g of x, y equals x squared minus y squared over x squared plus y squared. For all the two functions, we have xy approaching the point 0, 0. Prove whether or not the two functions are continuous at this point, at the point 0, 0. So let's try to solve this example or these examples together. So for a function to be continuous at a set point, we say that f of AB must be defined. Secondly, the limit of the function as xy approaches AB must exist, and then the limit of that function should be equal to the value of the function at the point AB. So we are going to check for all these three conditions. So for the first question, we have f of xy to be equal to 4x squared y minus 3x y squared. First, we are going to look out for f of 0, 0. And basically, we are going to substitute 0, 0 in place of x and then y in this function. So we have 4 times 0 squared times 0 minus 3 times 0 times 0 squared. And then 0 times 0 times 4 gives us 0 minus, this also goes to 0. So we have f of 0, 0 equals 0. Now let's move on to the limit. Now with the limit, we actually want to find or know how the function is going to behave as xy approaches the point 0, 0, but not equal to 0, 0. So we take the limit of the function 4x squared y minus 3x y squared as xy approaches the point 0, 0. Now this is a polynomial function, so it supports direct substitution. So we are going to directly substitute in 0, 0 in place of x and then y as we did here. So also we are going to have 4 times 0 squared times 0 minus 3 times 0 times 0 squared, and actually we are going to have the same answer, which is 0. Therefore, since the limits of the function f of xy as xy approaches 0, 0 exist and is equal to the value of the function at the point 0, 0, that is equal to the point, or is equal to f of 0, 0, we say that the function, therefore the function f of xy is continuous at the point 0, 0. The function is continuous at the point 0, 0. Now again, because this is a polynomial function, then it means that a polynomial function is always continuous at every point in the xy plane, because we have no restrictions on x and the y. So since this is also a polynomial function, it means that this function is also continuous everywhere in the xy plane. So now let's move on to the second example. For the second example, we have g of xy equals x squared minus y squared divided by x squared plus y squared. So first of all, we are going to look out for g of 0, 0. We basically substitute 0, 0 in place of x and y. We have 0 square minus 0 square, all divided by 0 square plus 0 square. This is equal to 0 divided by 0, and this is indeterminate. Indeterminate means we don't actually know what value this is going to be. I mean, we don't know what 0 over 0 is, so it's indeterminate. Now, since the value of the function is not defined at g of 0, 0, straight away we can conclude that this function is not continuous at the point 0, 0, because at least one of the conditions has been violated. Now, let's try to find the limits of this function, because it's going to be useful to us in the next example, even though the value of the limit is not going to change the fact that this function is not continuous at the point 0, 0. So we try to find the limits of this function, that is the limit of the function x squared minus y squared divided by x squared plus y squared as xy approaches the point 0, 0. So what we are going to do is we are going to approach the point 0, 0 from two different directions. So first of all, we are going to approach the point 0, 0 along the x-axis, and then we know that along the x-axis y is equal to 0, so we are going to put y equals 0. So we have f of xy, that is equal to f of x0, and then we have the function. This becomes x squared minus 0 squared divided by x squared plus 0 squared, and this is going to be x squared divided by x squared, provided that x is not equal to 0. So this is equal to 1. Okay, so when we approach 0, 0 along the x-axis, we have this to be 1. Again, let's approach the point 0, 0 along the line, this time along the line y equals x. So we have f of xy equals f of x, y is equal to x. So wherever we see y, we are going to substitute x. So for this function, we have x squared minus x squared divided by x squared plus x squared, and this is equal to 0 over 2x squared, and that is still 0. Now, since we obtain two different limit values for the two directions that we took, then it means that the limit of this function does not exist, because we have two different limit values for two different directions. So the limit of this function does not exist. Therefore, since the limits of the function g of xy, the limit of the function g of xy as xy approaches 0, 0 is not equal to the value of the function at the point 0, 0. We say that g of xy is not continuous at the point 0, 0. This function g of xy is not continuous at the point 0, 0. Now this is going to be useful to us in the next example. The limit of this function does not exist because we have two different limit values when we took two different directions approaching the point 0, 0. Now let's move on as we take the next example. So for the next set of examples, we are going to consider some piecewise functions. We are going to show whether or not these functions are continuous. So first of all, let's start off with example 3. So for example 3, we have the function f of xy equals x squared minus y squared over x squared plus y squared if xy is not equal to 0, 0 and 0 if xy is equal to 0, 0. Now for this function to be continuous at the point 0, 0, first of all we need to check if the function is defined at the point 0, 0. Now looking at the function, when x is equal to 0 and then y is equal to 0, we have the value of the function to be 0, which means that the function is defined at the point 0, 0. Now the next thing we are going to do is to find the limit of this function. So as I said earlier in the previous example, we said that for the limit of the function, we basically want to know how the function is going to behave when you have x and then y approaching the point 0, 0. So we take the limit of this function, which is x squared minus y squared over x squared plus y squared as x, y approaches 0. So we want to see how the function is going to behave when x, y approaches 0, 0 but not equal to 0. And then in example 2, you realize that the limit of this function did not exist. Therefore, we say that since the limit of the function f of xy as x, y approaches 0, 0 is not equal to the value of the function at the point 0, 0, we say that the function f of xy is not continuous. At the point 0, 0. Let's try some more piecewise functions. So here we have f of xy equals xy over x squared plus y squared if xy is not equal to 0, 0, and then 2 if xy is equal to 0, 0. Let's try this example as well. So first of all, we are going to see if the value of the function at the point 0, 0 is defined, and that is equal to 2 from the question. So that is defined, f of 0, 0 is equal to 2. The next thing is we want to find the limit of the function x times y divided by x squared plus y squared as xy approaches the point 0, 0. Let's see if this function exists and is equal to 2. So first, what we are going to do is we are going to approach the point 0, 0 from two different directions. So first, we want to approach the point 0, 0 along the x-axis. We know along the x-axis y is equal to 0. So we have f of xy equals f of x 0. Wherever we see y, we are going to substitute that for 0. So we have, for this function, we have x times 0 over x squared plus 0 squared. This is equal to 0 over x squared, provided x is not equal to 0. Then we say that this is equal to 0. So this is the value we obtain after approaching the point 0, 0 along the x-axis. Now the next thing is we are going to approach the point 0, 0, this time along the line y is equal to x. So here we have f of xy equals f of x, y is equal to x, so f of x, that is equal to x times x divided by x squared plus x squared. This is equal to x squared divided by 2x squared. This goes here once, this goes here once. We are left with 1 over 2. Now since the two values are not the same, it means that the limit of this function does not exist. So the limit of this function as xy approaches 0, 0 does not exist. Therefore, since the limit of this function, that is the limit of f of xy, where we have xy approaching the point 0, 0, is not equal to the value of the function at 0, 0, we say that the function f of xy is not continuous at the point 0, 0. Now let's move on to the next example. So for example 6, we have f of xy equals sine into brackets x squared plus y squared over x squared plus y squared if xy is not equal to 0, 0, and then 1 if xy is equal to 0, 0. Let's solve this as well. So first of all, we have f of 0, 0 giving us 1 in the question. So the value of the function is defined at the point 0, 0, and that is equal to 1. Next thing, we want to find the limits of this function. So the limit of the function sine x squared plus y squared, all divided by x squared plus y squared as xy approaches the point 0, 0. Now in this example, we are going to use what we call the polar coordinates approach. So how do we solve that using the polar coordinates approach? So what we are going to do is we are going to let r and then theta be polar coordinates, be the polar coordinates of xy. Now r here is called the modulus, and then theta here is called the argument from complex numbers. So what we are going to do here is we know that r squared is equal to x squared plus y squared, and then we are going to take r to be greater than or equal to 0. So from algebra we know that x is equal to r cos theta, and then we have y to be r sin theta. So basically we are going to substitute either r squared, x, or y depending on what we have as the function. So let's continue to find the limit of this function. So here we have the limit of the function sine x squared plus y squared all over x squared plus y squared. Now what we are going to do here is we are going to do direct substitution. So here we have the limit of the function sine x squared plus y squared is equal to r squared. So r squared all divided by r squared, and then here for this formula, as x and then y approaches 0, r also approaches 0, and then since r is greater than or equal to 0, it means that we are going to approach 0 from the right hand side. So let's substitute 0 in place of r. So here we are going to have something like sine 0 over 0, and sine 0 is 0, so 0 over 0 is indeterminate. Now the moment we have, after substituting the value of what the limit is approaching and then obtaining 0, 0, which is indeterminate, then it brings the idea of using the L'Hopital's rule. So we can use the L'Hopital's rule here. That is given by the limit. So first of all, let me have the formula here. So let's say you have the limit of a function. So the limit of a function f of x divided by g of x as x approaches, let's say, 0. Then using the L'Hopital's rule, we say that this is equal to the limit of the first derivative of the function f of x divided by the first derivative of g of x as x approaches 0. So basically this is the idea we are going to use here. So here we have, using the L'Hopital's rule, we are going to have the limit of, now let's try to differentiate this with respect to r. So when you differentiate what we have in the brackets here, we are going to have 2r. And then when you differentiate sine, you have cos, and then you repeat r squared divided by, for the bottom function, we are going to have 2r as r approaches 0 from the right. So 2r cancels out 2r, and then we are left with cos r squared. We do direct substitution of 0, and then we have cos 0 squared, which is equal to 0. So cos 0, and then cos 0 is equal to 1. Now notice that whenever your last expression depends on theta, it means that the limit of the function does not exist. And again, even if you obtain a real value for the limit of the function, it does not necessarily mean that the limit of the function is equal to the value you obtain. Whenever you obtain the limit of a function using the polar coordinate approach, it does not necessarily mean that the limit of the function is what you obtain. You will still need to use the precise definition of limit, that is the epsilon delta definition of limit, to prove that the value you had is actually correct. Now the reason why we are using this approach for this particular question is that the actual limit of this function is equal to the value we have here. The actual limit of this function is equal to the value that we have here. That is why we chose to use the polar coordinate approach. So the value of the limits of this function is equal to 1. Therefore, since the limit of the function f of xy as xy approaches the point 0, 0 is equal to the value of the limit at the point 0, 0, we say that the function f of xy is continuous at the point 0, 0. Now to the last question, question 7 or example 7, we have g of xy equals xy over the square root of x squared plus y squared if xy is not equal to 0, 0, and then 0 if xy is equal to 0, 0. Now let's try this together. So as usual, we first of all find g of 0, 0, and that is defined, that is equal to 0. Secondly, we want to find the limits of the function xy over the square root of x squared plus y squared as xy approaches 0, 0. Also for this example, we are going to use polar coordinates. So we know that x is equal to r cos theta, we have y to be r sin theta, and then r squared equals x squared plus y squared. So with this, we are going to have the limit of the function. We have x to be r cos theta times y, which is r sin theta. So we multiply the two, and then we have r squared cos theta sin theta, all divided by, and for the square root of x squared plus y squared, we basically take the square root of both sides, and then we have r to be equal to the square root of x squared plus y squared. So this is basically r. As r approaches 0 from the right, this is equal to, we are going to cancel out this r and then one of the r's on top, so that we have the limit as r approaches 0 from the right of r cos theta sine theta. At this point, you can do direct substitution so that we substitute 0 in place of r, so that we have 0. So we have 0 times cos theta times sine theta, and this is equal to 0. So the limit of the function as xy approaches 0, 0 is equal to 0. And notice that this is the required limit of the function. As I said earlier on, using polar coordinates to find the limit of a function does not guarantee that the value you obtain at the end is the limit or the required limit of the function. The reason why we used polar coordinates is just because for this particular question or for this particular function, the limit we obtain or the value we obtain is the actual limit of the function. So we have the limit of this function as xy approaches 0, 0 to be equal to 0. Therefore, since the limits of the function g of xy as xy approaches 0, 0 is equal to the value of the function at point 0, 0, we say that g of xy is continuous. This is continuous at the point 0, 0.